Hi, my name is Salma Najam, and this is my Physics Lab 1 on constant velocity. The purpose of this lab was to observe an object moving at a constant speed without changing direction and to create a computational model that describes the motion. We first recorded the object moving at a constant speed, uploaded it to Tracker, and used the data from Tracker to simulate the motion in Python. A fundamental concept necessary for this lab is that Newton's second law states that the acceleration of a moving object depends upon its mass and the forces acting on it. That means that the force and the acceleration are directly proportional. Newton's second law is calculated by equating the final velocity to the initial velocity plus the force over the mass measured over time. Since the object we're measuring today is moving at a constant velocity, that means it's not accelerating and the force is equal to 0, which means the final velocity would be equal to the initial velocity. We need to use the position update formula, which states that the final position is equal to the initial position plus the average velocity over time, since the force is constant. For this experiment, I rolled a soccer ball on the pavement. The soccer ball would be the system and everything around it would be the surroundings, such as the gravitational force and the friction. I then uploaded the video of the soccer ball rolling to Tracker. I started recording at 0.067 seconds, and as you can see, the ball moves in the positive x direction. Because of that, the slope of the position over time is a positive slope. Once I finished tracking the ball, I already had the initial position vector and I needed to find the initial velocity vector. I did this by finding a different position at a different time and calculating the change in position over time with my initial values and my final values to get my average velocity. I ended up calculating the average velocity to be 1.9 meters per second and inputted these values into GlowScript, which both had positive vector values since they were moving in the positive x direction. I also inputted my system mass, which is irrelevant in this case since the force is equal to 0, and I also put my initial time. I then added in my time step of 0.025 seconds so I can do a while loop where the computer will consistently re-update my change of position over time until my final time of 1.433 seconds was achieved. I put in the time into the while loop, and then in order for the computer to do the calculations, I put in Newton's second law and the update position formula in code form. And then I also put in the net force, but in this case, since the velocity is constant, it's 0. I then ran the code, and as you can see, the motion of the ball in the simulation turned out to be very similar to the motion of the ball that I recorded in Tracker. When you place the computational model versus observed position versus time graphs side by side, just like the previous slide, you can see that the computer does a pretty good job at simulating the motion of the ball. However, if you look very closely at the two slopes, you can see that there's deviations in between the lines, which could have been due to a rounding error in GlowScript's end, or could have been due to wind pushing the ball off course, or not clicking the center of mass as precisely enough when I was tracking the ball in Tracker. Another thing that you can see from this graph is that the computational model's slope is constant. It's moving at a steady rate. However, for the observed line, you can see that there's oscillations in the line, which proves that there's a non-constant velocity and that there is a force present, unlike the computational model, which proves that there is no force present. Let's say the axes were flipped. In this case, the magnitude of the velocity and position vectors would not be affected by this because in order to calculate the magnitude, you need to square the x component of the vector, and it wouldn't really matter if it was negative or positive in that case. However, when I was recording the ball, it was moving in the positive x direction to the right, and if I flipped the axes, then it would be moving to the left in the negative x direction and therefore would lead to a negative slope. As for the force, we do know that there's a gravitational force pulling down on the ball. There's a normal force and tension when the ball is rolling across the pavement. However, we don't know the exact values of the force, and there could have also just been a force when the ball was pushed in the first place. So no, there is no way to actually determine how many forces contributed to the overall zero net force. Thank you so much for listening to my Physics Lab 1 presentation. Have a good day.